It is a great pleasure and honor to welcome you to the second morning session here at the Heidelberg Laureate Forum. My name is Dirk Schleicher. I am professor of mathematics at Jacobs University in Bremen. And as a member of the scientific committee of the Heidelberg Laureate Forum, I'm involved in selecting the young scientists that are participating here. And I want to tell you, it's always a great pleasure and great honor to first see all the wonderful applicants, and then you meet you all in person and see that you all live up to the expectations you raised in your applications. So it's very wonderful for you to see you here all in person. It is a great honor for me to introduce the first speaker of the session, Len Adleman from Southern California, who won the Turing Award. It's the most notable award of many, 2002. So it's known not only to the computer science community, but to every mathematics and computer science students, at least through the initial of his name, the R from the RSA algorithm. He worked in many different fields between primality testing and even biocomputing, but he confessed to me just a moment ago that at heart he always thought of himself as a mathematician. And as such, he is going to present the results Strata in complex analysis. It's a great pleasure to have you here. Thank you.
Thank you very much. It's a pleasure for me to be here. I want to begin by thanking the Klaus Tschira Foundation and Klaus Tschira for his vision and support of science and for putting this wonderful conference together. I'm going to talk about work done with my graduate students, in particular Dustin Reicius, Joseph Biebel, Henry Yoon, Rolf Schmidt, among others. And though we're all computer scientists, we somehow, pretty much by accident, ended up on a journey into complex analysis. And when we began that journey, we sort of had a choice. We knew no complex analysis beyond what you get in your normal education. So we could have learned some complex analysis and stood on the shoulders of giants, or we could have just tried our luck. And so perhaps unwisely, we tried our luck and didn't learn much complex analysis. So we spent most of our time lost in the woods, dazed and confused, despairing of ever finding our way out, which for you young mathematicians and theoreticians, this is part of your life in the future, being dazed, confused, and despairing of ever finding your way. But you do it, the struggle's worth it, because occasionally you see something beautiful. We've been at this journey for about 10 years now, and my talk is essentially a sort of photo album of the things we've gotten to see along the way. There won't be an exam after this talk, so don't worry if you're not following it. Follow as much as you'd like, or as little as you'd like. Hopefully, it'll be an enjoyable journey. I managed to misplace the pointer already. All right, hang on. We ended up studying complete analytic functions and their topological cousins, Riemann surfaces. And these are due to Weierstrass and Riemann in the middle 1800s. And we're not the first ones to be attracted to the beauty of Riemann surfaces. They're mathematically beautiful, but also they're aesthetically very pleasing. So this is a picture of a Riemann surface of no particular mathematical interest, but we just liked the way it looked, and we named it the Orchid, and it's now on the front of the book we've written about our journey. If you, at the end of this talk, would desire a PDF of our book, just email me at that address. Here's some more Riemann surfaces. The one on the left is the Riemann surface for the square root function. And you'll notice it seems to have sort of two layers. That's because the square root function is double valued, right? 4 has 2 square roots. One of them's -2. And that's the thing about Riemann surfaces. They're a way to study functions from the complex numbers to the complex numbers that are analytic, differentiable, and which are multi-valued. And on the right there is another pretty familiar Riemann surface. It's the one associated with the log function. And because the log is infinite valued, the log of 1 is 0, but it's also 2 pi I, 4 pi I, and in general, k pi I, where k is an even integer. It's actually infinitely many levels. At the top is a image of an elliptic curve, and I won't go into why it's not being shown as the classic torus. In the middle is just something we just stumbled across and thought was cool, and at the bottom is the orchid. Now, ever since Riemann surfaces arose, mathematicians have been taking out conceptual scissors and cutting them into flat sheets. And that's what we're going to do, cut them into flat sheets, so there's nothing new there. But we're just going to be very organized about the way we do it. And hopefully it's what we do with the resulting sheets, which we then call strata, which may be of interest. So if you're going to start studying Riemann surfaces, one good place to start is to look at failures of analyticity, places where the function doesn't, in fact, have a derivative. You would think that you could look up a definition of what a failure of analyticity is on a Riemann surface. But if such a definition exists, I've never seen it. And, well, I was shocked, and maybe I'm wrong, you know, but I never found such a definition. Gent, I should have asked you. Right. Cancel the talk. All right. So anyway, let's start by looking at a certain class of failures of analyticity. So here's an image of the function f of z equals 1 over z. And famously, it has a failure of analyticity, no derivative at 0. And it's sort of the simplest failure of analyticity one can imagine. It's a simple pole. It can be described with a Lorentz series of inner radius 0. And those failures of analyticity that can be described with a Lorentz series of inner radius 0, we're going to call, just for the purpose of this talk, 1 failures. Now, if we take this function, compose it with sine, and invert it, we get this function. And you can see that it's more complex. And so what's going on here is there are actually infinitely many failures of analyticity in that picture, all of which are 1 failures, but at 0 in the center, they're accumulating. Okay, and so that failure of analyticity can't be described with a Lorentz series, and so we're going to call it a 2 failure of analyticity. And if we continue this process, we're going to compose with sine, invert, we get this function. And now you can see things are becoming even more interesting. And now what we've got is infinitely many 1 failures of analyticity that are accumulating to infinitely many 2 failures of analyticity that are accumulating at 0 to something new again, and we'll call that a 3 failure of analyticity. We'll do one more step, 4 failure of analyticity by composing with sign and inverting. And you can see that it's becoming more complicated at 0. And so much so that our ability to render it failed. All right. And so as you move up this ladder, the failures of analyticity are becoming more daunting. Okay, so one can imagine that a billion failure of analyticity, do this a billion times, would be a pretty daunting thing. Okay, but in fact, it's child's play, because what happens is the whole thing goes transfinite. All right, and so there's an omega failure of analyticity, where omega is the first infinite ordinal. And then there's an omega plus 1, omega plus 2, omega squared, all the usual things, right? And one begins to wonder, is this ever going to stop, right? Well, fortunately, the wave breaks and rolls back at omega 1, which is the first uncountable ordinal. So there is an omega 1 failure of analyticity. What it looks like, don't have a clue. But I know it exists, and I know that there's no omega 1 plus 1 failure of analyticity, right? So that's the worst this class can get. All right, so this notion of this kind of failure of analyticity leads to some of the local objects in our theory. So what we do is we consider analytic functions on a disk, which at their center have their worst failure of analyticity. And let's say it's a theta failure of analyticity, where theta is some ordinal, less than or equal to omega 1. And we call such a function a generalized power series of level theta. So we have all these generalized power series. And those are some of the local objects in our theory. Now, roughly speaking, the only kind of other failures you can have on a Riemann surface are either those that arise from natural boundaries or branch points. And to a large extent, we can't handle any of that stuff except one small instance, which is if you have isolated branch points, whether they're arithmetic or logarithmic. Then we can make some progress. So we're going to need some more local objects for our theory, and I'm going to explain how we get them. At the same time, I describe this process of stratifying a Riemann surface. And in particular, we'll choose the orchid as our victim. And the orchid is given by f of x equals that, which makes it a 4-valued function. It's not too important what it is. But here's how you stratify it, and here's how we get new local objects. So to stratify the orchid, we do a process called harpooning. Okay, so you take a harpoon, and you get to choose the diameter of the cylinder that's going to be its handle. And then you walk up to the orchid, and you throw it through the orchid. You throw the harpoon. And what it's going to do is it's going to cut away, in this case, 4 disc-shaped segments out of the orchid. And here's what you get. Well, typically you get what you see on the right here. You typically get 4 disc-shaped segments. These may look like they're touching each other, but in fact they're not. And each of those disc-shaped segments is a generalized power series. So we can account for it in our local theory. But if it's the case that you happen to have thrown your harpoon so that the point went through the tip of the harpoon went through a branch point on your Riemann surface, then what you get is 4 discs, but they may be stuck together. some of them. And they're stuck together by analytic continuation. Now, it's at that point that we're going to take out the scissors and we're going to cut into small discs. So as described or shown on the left, when you cut a stuck together pair of discs, you necessarily create a discontinuity, which is indicated by the color discontinuity on the screen. But these objects, the ones on the left, are what we call core strata, and they're the other objects in our local theory. So we have the generalized power series and the core strata. Okay. Now, we then define a notion which is like analytic continuation, but allows us to go right through branch points, and we call that prolongation. And so we can prolong through branch points, and then we use that to develop an equivalence relation on these local objects. And the equivalence classes then are the strata. Okay. So in the case of the orchid, the strata we get are shown there. There's the 4 strata, and you can tell by the color discontinuities that there were branch points on the orchid. Now, you'll notice that I've made the 4 strata nodes in a graph, and the edges are labeled with -I or 0. And those labels are because the orchid has branch points at -I and 0. And essentially, those labels tell you, the colors would also tell you, by the way, how you should glue those 4 strata together to get back to the original orchid. But implicit in that graph is a group. And it's related to, but not the same as, the fundamental group of the orchid as a topological object. So every Riemann surface that we stratify is going to acquire a group. This particular group is a finite group, and it's non-abelian. Right. We call this graph the album of the orchid. So here's another album. This is the album you'd get from the log function. The nodes, the edges are labeled with 0 because the log only has a branch point at 0. And this stretches in both directions to infinity, so its corresponding group is going to turn out to be isomorphic to Z. It's going to be cyclic, therefore. And here's another album. This is for the x to the pi over 2 function. You know, complex analysis, you can do that kind of thing, x to the pi over 2. And it has a album. Again, its only branch point is at 0, and its group is again Z, so cyclic. Here's a more elaborate example. This comes from the log of x times the log of x minus 5 function. It's a 2-dimensional grid of strata, and it is going to end up corresponding to Z cross Z as its group. Now, it's at this step, yes, I mentioned that we can't handle really perverse singularities. So if your Riemann surface has something like the top or something like the bottom, we won't be able to stratify it. So the top is showing what we call a scar or a 2 blemish, which is what happens when branch points accumulate to a single point. And we can't deal with that. Love to be able to, but we can't. And then on the bottom is a Riemann surface, which can be cut into 2 sheets. The one on the left looks really pretty and could be a stratum. The one on the right looks like a stratum that somebody shot a bullet through, and that is a stratum with a natural boundary in it. So if your Riemann surface has these kind of perverse failures of analyticity, we can't stratify it. But of all the Riemann surfaces that we can stratify, we now do the following. And if we really parted paths with the traditional development of complex analysis, if we have, it probably occurs here. What we do is we take all the strata from all of the stratifiable Riemann surfaces. Like some may come from square roots, some might come from the orchid or the log or the square root of the sine of 1 over the Riemann zeta function. Okay? And we're going to take them all. You should always mention the zeta function, giving an analytic, talk in complex analysis, like you might have some clue as to what's going on. I have none. Anyway, but we're going to take all those strata, and we're going to put them in a blue cylinder labeled strata, okay, as illustrated here. Now, because we were very careful about the way we cut these strata, or cut the Riemann surfaces, these strata have a natural addition operation under which they're closed. They're also closed under subtraction, closed under multiplication, and except for the zero strata, they're invertible, okay? So they're forming a field, yes? In addition, they're closed under differentiation. And in addition, they have an operation which is a lot like composition of functions, but a lot more difficult to deal with. We call it blend. And blend sort of like composition of functions, but for example, it's non-associative. So it's really difficult to deal with, but it's the key for us being able to learn about the field of strata. Okay, so at this point, we've created a situation where we have a strata field theory, right? And that strata field theory, you have the field of strata, and it has a subfield, for example, the meromorphic strata, which you can think of just the meromorphic functions. And it's got all sorts of extensions. And those extensions can be finite or transcendental extensions. And most, whatever that might mean, of them that we're interested in are transcendental. Okay. Now, these kind of lattices of fields occur all over mathematics. And one interesting place, an important place they occur is in algebraic number theory. So in algebraic number theory, we have the algebraic numbers that form a field. And at the bottom, or a subfield of that, is the rationals. And we have all sorts of extensions. In this case, they're all going to be finite extensions. And some of them are going to be Galois, some are not going to be Galois. Those that are Galois, some are going to be abelian groups, and some are going to be cyclic groups. And of course, algebraic number theory is one of the pillars of number theory. And one of the most important theorems in algebraic number theory is the Kronecker-Weber theorem, which says that there are some special fields. Okay, they're the cyclotomic fields. And the cyclotomic fields, of course, are gotten by adjoining roots of unity to the rationals. And what makes them special is, of course, every element in a cyclotomic field is living in an extension that's Galois and abelian. But more important is that every algebraic number that's living in a Galois abelian extension of the rationals is a member of one of the cyclotomic fields. And the reason that's important is because, one, it is a very nice way to prove quadratic reciprocity using this result. But there's hundreds of ways to prove that. But this is also the way one goes about, and was really probably motivated by the desire to prove higher reciprocity laws. And then it also is the sort of first step in what became class field theory, and which gave us, I assume, the most general reciprocity laws we've known, Arden reciprocity law. And so that's the situation. Now, the question arises is, we've got strata field theory, and there's algebraic number theory. Is there more meat to this relationship than just another tower of fields? And so the answer seems to be yes. Okay, so back to strata field theory, there's an analog of the Kronecker-Weber theorem, which is the following. So there are fields called log polyfields, called by us log polyfields, and they're the analogs of cyclotomic fields. So a log polyfield is obtained by taking your favorite polynomial h with complex coefficients, it shouldn't be constant, and taking the log of it. Okay, now that function has a Riemann surface associated with it, and it's stratifiable, and you can take the strata and you can, what we call, attach the strata to the meromorphic functions. Now, attach is an analog of the more familiar adjoin. Okay, but it's not the same thing. Adjoin's not the right thing, and M attached log of h is not the smallest field that contains both M and log of h, but there's a right notion. Okay, now what makes these log polyfields important is that, one, every stratum you find in a log polyfield came from a Riemann surface that had a cyclic group. We're only doing cyclic here. Had a cyclic group. But the harder thing to prove is that every stratum you get from every Riemann surface that has a cyclic group is in a log polyfield. Right? So that's the analog of the Kronecker-Weber theorem. And the take-home message of that, at least to us, this is what we've taken home, is that strata field theory is going to be interesting. It's going to have structure. And we've spent our time since this, A, writing the book, which proves this, and B, just exploring a little bit more of strata theory. So I'll briefly describe what we've looked at and seen. Okay. Oh, well, I'll skip this. Okay. So we've gone a little further, and it turns out that if you go to one of these field extensions, you'll find in there a nice ring. And in that ring, you'll find a structure analogous to the Picard group, class group. Okay. So all that is very natural in the strata setting. There's a Galois theory in that subgroups are going to correspond to subfields, sort of, because there's something else going on that we really can't figure out. We also, looking at what we could call strata class field theory, we believe that in addition to handling cyclic groups, with the Kronecker-Weber theorem, theorem that I showed you, we think we can actually handle some non-abelian groups as well. So maybe develop a sort of non-abelian class field theory in this world. We also have looked just a little bit into algebraic geometry. So by considering finite extensions of the meromorphic, you can consider the usual objects of algebraic geometry, y to the n equals g of x, for example. But because transcendental extensions are there, you can also consider other curves like e to the y equals g of x, okay? And e to the y equals g of x, where g of x is a polynomial, is intimately related to these log polyfields. And inside those log polyfields, we have analogs of Picard groups. So there should be something analogous to the Jacobian of such a curve in this world, but haven't explored further. We have some topological things, which I'll skip. What we've spent most of our time on, and this is joint work with Sheldon Kamieni and Burden Newman, what we're spending most of our time on is trying to move results from strata field theory back down to algebraic number theory. And we're trying to follow the plan laid out by Kronecker, wherein he was able to sort of tell us explicitly what the class fields of imaginary quadratic fields were. So that approach is based on taking a cubic polynomial, taking its square root and inverting it there. And that gives rise to a Riemann surface, which can be sort of cartooned in this way. Then you take the antiderivative of this Riemann surface, get another Riemann surface. Then you take its compositional inverse, and you get the Weierstrass P function. This is all classical elliptic curve stuff. You get the Weierstrass P function, and then Kronecker taught us that by taking torsion points on certain elliptic curves, we can get the class fields of imaginary quadratic fields. So what we're trying to do is our machinery allows us to very easily deal with, say, starting with a quintic polynomial, or more generally, any polynomial, taking its square root and inverting. And then we can still take, for this Riemann surface, its antiderivative, and we can no longer take a compositional inverse, because that doesn't make sense, but we can take a blendicative inverse related to that blend operation that I mentioned, which is sort of the substitute for composition in this world. And what we get is a Riemann surface and something we'll call a generalized P function. And so what this is it's a analytic function which is quadruply periodic. And I know the immediate reaction is there are no such things, but that's only, of course, on the plane. They exist on Riemann surfaces. And we would like to look at torsion, but there's no group. So hard to find torsion, but there are torsion-like things, and we're sort of hoping that we can exploit that to build maybe some explicit class fields for, say, quartic extensions. But that's just the path we're taking. It went really well at the start, but we're right now back in the woods, lost, dazed, and confused, which is where we started. All right, I think I'll stop there. Thank you.
Thank you very much for your beautiful presentation. We have a lot of time for questions or comments from the audience. Well, let me start with a young laureate. Just
yeah, sit down, Stephen.
Young, okay, whatever.
So have you found any applications to computational complexity?
No, the goal was not algorithmic, and but we do have a couple of algorithms that have just sort of popped up that we can use to find out certain things about elliptic curves and hyperelliptic curves. Maybe they'll be useful, but no. Yeah, but I think we're on the verge of settling that problem you stated one time.
Which problem was that?
I think NP equals, yeah. All right, I forget. Anyway, yeah.
I'd be happy with much simpler lower bounds if you
Me too. Yeah.
There was another question very nearby. Yes.
I'm going to ask a question about the maths in a way.
Yes.
Now, it seems like what you've done is you've produced some, you've been working on the local theory of the power series and their algebraic analogues of algebraic number theory. Now, I came across about a year ago a very old theory, which I don't know if you've heard of these things called Poisson series.
Yes.
Yeah, and one thing which I thought was really interesting there is that you form another field of Poisson series, which is an algebraic closure of your power series.
Yes.
And you can study them geometrically through Newton polygons.
Yes.
Right, and have you found any ways in which, the geometric study of Newton polygons and objects like this can be related back to the number theory and the Galois theory? Like, how would this, does this fit in at all to your study of abelian extensions?
Right. I don't have an answer to what you're saying, but I do have a remark on it. So I'll do the best I can here. Okay, so so first of all, generalized power series are not amenable to any of these things. They don't have series representations that I know of. But you're talking about sort of the, to some extent, the history of series in mathematics. So, power series look like this, and they describe things like that. I'm being informal. And Lorentz series look like this. They have so-called, the ones you want to consider have finite, they have infinite principal part, or allowed to, and they describe bad things. Anyway. And then you're talking about the Newton-Poisson series. Now, the Newton-Poisson series are interesting, but they only allow you a finite principal part. We've extended that to what we call world series.
Yep.
Yeah, well, yeah. And where we allow an infinite principal part. And the value of that is it lets you describe multi-valued functions on an annulus. Okay. And the value of that is that there's a generalization of Cauchy's famous residue theorem. These series have residues. These series are, by the way, very computable if you want to study a hyperelliptic curve or something. Okay. And for example, if you're studying elliptic curves, then you can have a generalized power series which will tell you what happens when you integrate around a pair of points, branch points, and it'll have a residue on it. In this case, it will have a residue, not always. But if you collect that residue and you go around then another pair of points and take all possible pairs, you collect the residues, then what you get is, up to 2 pi I, you get the basis for the lattice that we associate with the elliptic curve. So we've tried to exploit these world series, and they seem very, very useful. But beyond that, in terms of answering your question, I can't.
Oh, that's fine.
All right, thanks. All right.
Thanks.
Yeah. Hi.
What symbolic computation tool will you use for obtaining these results and generating the graphics? Do you use Mathematica or some other one?
I use the tool called Graduate Students. It really is a great tool. I tried doing this myself with Wolfram's stuff. I could do okay, but some of these images are really tough. And my graduate students do it, and they've used a lot of things. They've used Mathematica, and they've used 3 or 4 other programs to try to get it all working. So I'll try to get that information if you'd like it from my graduate students.
I would like it.
Yes, okay.
Do we have more questions from the audience, especially from the young researchers? Yes.
I guess following up on Steve Cook's question, are you aware of any cryptographers looking into applications of strata field theory, or do you think this would be a productive area to explore?
Okay, so the answer to that is, since you just witnessed the first talk after 10 years of study, no one knows about this at all, right? So I don't think people have tried to do very much with it. It seems to me it's pretty distant from cryptographic sort of issues. We'd be very happy if we can transport some of the ideas in strata theory down to algebraic number theory. If we could do that, then maybe they would have applications, but that's very distant, seems to me.
Okay, then I think it's time to thank our speaker one more time.
Thank you. Thank you.